Hi everyone. Today we are going to discuss one of the important methods to find out the solutions of algebraic and transcendental equations, that is Newton-Raphson method. Let us look at the procedure to find out the iterative formula using Newton-Raphson method, and we will discuss about its convergence. We will also see one example of finding the root of the given equation. For this, let us assume that we have an hypothetical equation f of x is equal to 0. For this, we need to find out the solution. Solution means that satisfies the equation. Now, let x naught be the initial approximation to the root. Let x naught be the initial approximation to the root. So, we will choose an initial approximation to the root, which is given by x naught. Now, let us say that x1, which is equal to x naught plus h, be the actual root of the equation f of x is equal to 0. Let x1 is equal to x naught plus h be the actual root of f of x is equal to 0. Right? Since x1 is equal to x naught plus h, b is the actual root of f of x is equal to 0, we have, what do we have? F of x1 is equal to 0. This implies what we have? F of x naught plus h is equal to 0. Now, what is this f of x naught plus h is equal to 0? If we apply the Taylor series expansion of f of x about the point x1, what we have is f of x1 is equal to f of x naught plus h. This is equal to f of x naught plus h into f dash of x naught plus h squared by 2 factorial f double dash of x naught plus and so on. H cube by 3 factorial f triple dash of x naught plus and so on. This is what we get. But here, generally, we choose an initial approximation to the root, which is close, very close to the actual one. That means what we want to say is here h is very, very small. Let x1 is equal to x naught plus h. That's what we have chosen. That is the actual root. Okay. Since we choose an initial approximation to the root, which is very close to the actual one, okay, here h is very small. And in the Taylor series expansion, we will neglect the second and higher order terms. Since h is very small, h square is very, very small, h cube is small, h power 4 is small, and so on. And even you can observe that in all these things we are applying the dividing the terms with the factorials, right? So we neglect the second and higher order terms in the expansion. Since f of x1 is equal to 0, so here what we are doing now, we are neglecting all these second and higher order terms. Okay. Now we have f of x1. This is equal to f of x naught plus h. This is equal to f of x naught plus h into f dash of x naught is equal to 0 by neglecting all the remaining terms. This implies I am able to calculate the h value from this, which is minus f of x naught by f dash of x naught. Okay. Now what I will do is I'll bring this h value into my relation, which is x1 is equal to x naught plus h, and bring this h is equal to minus f of x naught by f dash of x naught into the relation x1 is equal to x naught plus h, and this gives my initial first approximation to the root. So therefore, okay, therefore what we have, okay, I can write therefore x1 is equal to x naught minus, right, f of x naught by f dash of x naught. So this is called the first approximation to the root. Now like this, we will continue with like this, we have the second approximation. Now it is given by x2 is equal to x1 minus f of x1 by f dash of x1. This is called what? This is the second approximation to the root. Okay, and the process is continued until two successive approximations are the same, and so on. Now I am writing the n plus 1 approximation to the root, which is given by xn plus 1 is equal to xn minus f of xn by f dash of xn. So this is called the Newton's, right, iterative formula. So what is our formula now? Xn plus 1 is equal to xn minus f of xn by f dash of xn, right? And this works well when the initial approximation is very close to the actual root. And one of the important advantage of the Newton-Raphson method is the Newton-Raphson method converges fast compared to all the previous methods, that is the bisection method, false position method, iteration method. Okay, so compared to all other methods, the Newton-Raphson method converges very faster. In very less number of approximations, we'll get the root correct to the required number of decimal places. Okay, now let us look briefly about the convergence of this Newton-Raphson method. Okay, now to talk about the convergence of the Newton-Raphson method, okay, let me start with the condition that we have in the iteration method. Okay, for that, let us assume the Newton-Raphson iterative formula, which is xn plus 1 is equal to xn minus f of xn by f dash of xn. When you look at all these different things that we have on the RHS part, they are all something like x is equal to some phi of x. So this part is now, this is what we are calling it as, yeah, this is the one. Yeah, this part we are now calling this as, what is this called? This is our phi of x. Okay, this is our phi of x. Now using the iterative method, what is the condition that we have? Modulus of phi dash x less than 1. So for that, let us find out the derivative of this phi of x. Okay, so they are all something like x is equal to some phi of x. Okay, now what I am doing now, I am calculating phi dash of x. So for the RHS part, I am just calculating the derivative. Okay, now while calculating the derivative, so with respect to x, the derivative is 1. Now I have something like f of x by f dash of x, which where we can apply u by v rule. Okay, so v u dash, so this will be f dash of x into f dash of x minus f of x, okay, and then f double dash of x, and then this entire term divided with f dash of x whole square. Okay, right, now when we divide, when we separate these terms, yeah, this is f dash of x into f dash of x, which is f dash of x whole square, okay, divided by f dash of x whole square, which will be 1, so you can cancel these two, and minus of minus, this will be plus, and we will be left with f of x into f double dash of x. So therefore this leads to this is equal to now f of x into f double dash of x, okay, divided with f dash of x whole square. This is what we have. Now, what is our condition for the convergence of the iteration method? Modulus of phi dash x less than 1. So this implies what we have, f of x into f double dash of x by f dash of x whole square, right, is modulus of this is less than 1. Okay, and then this leads to our convergence, which is given by f of x into f double dash of x less than f dash of x whole square. Okay, so modulus of f of x into f double dash of x less than modulus of f dash of x whole square, right? So this is our convergence formula. Okay, so once again, let us look at this. So to determine the convergence condition for the convergence of the Newton-Raphson method, we will take the Newton-Raphson iterative formula, and this is something like x is equal to phi of x, right? Where we find the derivative of that phi of x. Now we call it as phi dash of x. Now phi dash of x gives this value, right? U by v formula we have used, and then here we'll be left with f of x into f double dash of x by f dash of x whole square. And what is our condition for the convergence? Modulus of phi dash x less than 1. And this leads to f of x, f double dash of x less than f dash of x whole square. So this is the condition for the convergence of Newton-Raphson method. Okay. Right. Now, let us take an example on this. Let us go to an example. Let me choose a different color over here. The question is, find a real root of sin x is equal to 1 plus x cube using Newton-Raphson method. Newton-Raphson method, Newton's method, Newton's iterative method, Newton-Raphson method. These are all they are all the same. They represent the same. Okay, keep that in mind. Okay. Now let us see what is our f of x here. Let us look at the solution part. Let f of x is equal to, I will write this as sin x minus 1 minus x cube is equal to 0. Okay, so this is my function f of x, right? And when some trigonometric functions are present in the given equation, see that in your calculator you are putting all the things in the radians, right? You are doing it in the radians when we find some trigonometric functions in the given equation. Okay, so set your calculator in the radians and try to do the things. Okay, try to calculate. Now I am calculating f dash of x derivative for this, which is cos x minus 3x square. Okay, this is my f dash of x. Now what is my iterative formula? Xn plus 1 is equal to, okay, xn minus f of xn by f dash of xn. This is my iterative formula. Okay, now first I have to choose an initial approximation to the root. I have to choose an initial approximation to the root. Okay. Now for that, I can just find out an interval first where the root lies. Okay. For that, what I observed is at x is equal to 1, at x is equal, sorry, minus 1, at x is equal to minus 1, f of minus 1. I have just substituted x is equal to minus 1 in the given equation. The answer is minus 0.8415. This is the answer. Okay. Similarly, at x is equal to minus 1.5. I have substituted x is equal to minus 1.5. So f of minus 1.5, this is equal to 1.3775. These are the values I am getting when I substitute x is equal to minus 1 and x is equal to minus 1.5 in the given equation. Okay, I have chosen specifically this example because for this example, one of the root is negative. That's why I have chosen this example. That means what we observe is a root lies between minus 1 and minus 1.5. A root lies between minus 1 and minus 1.5. Therefore, okay, a root lies between minus 1 and minus 1.5. So what will be our initial approximation? So you may choose it as some minus 1, you may choose it as minus 1.5, you may choose it as minus 1.2, minus 1.3, minus 1.4, anywhere in this particular interval. The best choice of choosing the initial approximation is taking the midpoint of the interval. Okay, so I may start with minus 1.2, I may start with minus 1.25. That's our choice. Okay, maybe one approximation may increase or decrease. This may happen. Okay, so I'll start with minus 1.2 as my initial approximation. Let x naught is equal to minus 1.2 be the initial approximation. Be the initial approximation to the root. Let x naught is equal to minus 1.2 be the initial approximation to the root. Now what I will do, I will substitute, okay, in the iterative formula all these things, right? So what I have now, so let me write the first approximation. So therefore the first approximation is, okay, x1 is equal to x naught minus f of x naught by f dash of x naught. F of x naught by f dash of x naught. What is my x naught? Minus 1.2 minus, what is my f of x naught? Sin x minus 1 minus 1.2. So sin of minus 1.2, okay, minus 1, right? Minus of minus 1.2 whole cube, okay, divided by, what is its derivative? Cos x minus 3x square. Cos of minus 1.2, okay, minus 3 times minus 1.2 square. Okay, now the answer to this is given by minus 1.2516. This is the answer. Okay, minus 1.2516 is the answer. So I have taken x naught as minus 1.2. That is my initial approximation. You may begin with minus 1.25. You may begin with minus 1.3. Okay, somewhere which is close to the actual root. So I have taken approximately the midpoint. Okay, and here x naught is minus 1.2 minus sin x minus 1 minus x cube, that is our given function, divided with cos x minus 3x square, right? Now the answer is minus 1.2516. So this is my first approximation to the root. Now let me move to the second approximation to the root. Second approximation to the root. So what is the formula for the second approximation? X2 is equal to x1 minus f of x1 by f dash of x1. Okay, already you know the formula, already the function is available, and the previous approximation is just present in the previous step, isn't it? Okay, so yeah, this is equal to minus 1.2516 minus, okay, I have now sine of minus 1.2516 minus 1 minus of minus 1.2516 whole cube, okay, divided by cos of minus 1.2516 minus 3 into minus 1.2516 whole square, right? So this leads to our value, and that gives the second approximation to the root, which is given by minus 1.2478. I have just rounded off to the 4 decimal places here. Okay, you can increase the number of decimal places, right? So that the accuracy on the root converges faster. Okay, right? So this is my second approximation. Now let me take you to the third approximation to the root. Third approximation. So in third approximation, I'm once again writing the formula x3 is equal to x2 minus f of x2 by f dash of x2. Okay, and this is equal to minus 1.2478. The same thing I'm doing once again. Okay, sine of minus 1.2478 minus 1 minus of minus 1.2478 whole cube, okay, divided by cos of minus 1.2478 minus 3 times minus 1.2478 square. And what is our answer to this? This is now minus 1.2491. Okay, this is my third approximation to the root. See here, in just two steps, we observed that in the third approximation, the root is correct up to 2 decimal places. Now let me uh, complete the fourth approximation also, and let us see what is going to happen here. Okay, so when I do the fourth approximation, x4, okay, the formula is x3 minus f of x3 by f dash of x3. So this is equal to, again, I'll substitute all these things and just cross check it, okay, whether you are getting the same answer or not. And we say that the root is correct up to 4 decimal places. Okay, and this is the advantage of the Newton-Raphson method. Okay, hardly in 3 or 4 approximations, right, depending on the initial approximation that we are choosing, uh, the Newton-Raphson method converges faster when compared to the previous method. When we solve the same problem using any of the previous methods like the bisection or the false position, okay, they may take more number of approximations, more number of iterations need to be done. Okay, so therefore what we conclude here finally, okay, since x3, okay, and x4 are identical, okay, are equal up to 4 decimal places, 4 decimal places, okay, the root is minus 1.2491. Okay, so this is using the Newton-Raphson method, and this is the example that we have chosen. Let us look at it briefly. I have taken one example. This example specifically I have chosen because for this example there exists a negative root. Okay. I observed that a root lies between minus 1 and minus 1.5. Okay, and since we have some trigonometric function present in the equation, set your calculator in the radians and find out the functional values. Okay, now I have chosen my initial approximation x naught as minus 1.2, right, and I have obtained a sequence of approximations x1, x2, and x3, right, and also x4, and I observed that the root is correct up to 4 decimal places. Okay, so therefore the actual root of the equation is minus 1.2491. You may start with minus 1.25, maybe one approximation may reduce, right? You may start with minus 1.1, minus 1.3, something like that, and that gives our answer. Hope you understood and hope you liked this video. Thank you all.